You will make an oral session here?
Yes.
That's okay. Yeah, it's oral session.
Do you need a room? No.
No.
Do you need a room?
No. They are asking for to enter the session. It's oral session.
If you want to learn.
Hello? Ok, chi deve presentare?
Presento io per primo.
Sì.
No, devo
Caricare. Sì.
Io non so una
Questo è un problema. No, io neppure, nel senso.
Anche perché magari possiamo chiedere se c'è qualcuno da remoto.
No, qua. Hello, good morning. We are ready to start with this last session of the ICCSA conference. Can you hear me? We can't hear you. Simone Rebegoldi, I can't hear you. So maybe if you entered the room through Internet Explorer, or you should use ok, non è più Internet Explorer, è Microsoft Edge. Okay, so you should switch to Google Chrome. Ok, intanto che rientra, solo una cosa. Quando dovete poi presentare da qui per la condivisione, avete già visto come si fa qua? Entire screen, selezionare lo screen e share. Okay. Per qualunque cosa sono di là.
Hai detto stanza? Grazie.
Figurati. A dopo. Ciao, grazie. Questo è il mio.
Beh, cominciamo.
Okay, it's written. the email.
Scusa, il gruppo Floriana.
No.
Le mettiamo sulla carta.
Eccoci Simone, ci senti? Noi non ti sentiamo ancora, sai?
Ma non è che l'audio del computer basta.
Ma aspetta.
No, quello del computer penso.
E qua è al massimo. Prova ancora Simone? Scusa, c'è qualche problema tecnico con l'aula. No. Prova a vedere se il tuo microfono è selezionato giusto, se magari hai un paio di cuffiette che ti possono fare... Io ti vedo mutato proprio, come se avessi il microfono spento. Ora prova. Ci senti tu? Noi non ti sentiamo.
Chiama l'assistenza.
Sono io l'assistenza.
Tu sei il CERT.
Provo con lo smartphone, va bene?
Abbiamo le presentazioni.
Ah, ottimo.
Presenta anche lui.
Simone, se sei d'accordo, nel frattempo farei presentare il secondo speaker della sessione e così poi magari proviamo a risolvere la cosa. Comunque tu ci riesci a sentire, quindi riesci a seguire la sessione. XA, no?
No, dentro UXM.
No, adesso sentono.
Adesso mi sentite?
Ci senti? Puoi parlare Simone? Giusto per fare una prova?
Allora, mi sentite adesso?
Ecco, ora sì. Ciao
sì.
Simone, come
Ciao.
stai?
Buongiorno,
Ciao.
bene, grazie. Mi
Piacere
scuso,
rivederti.
non so quale sia il problema. Allora, l'unico problema che ho adesso è che devo recuperare le mie slide.
You need the keyboard.
Yeah, because
Se vogliamo parlare su-
Ok. E
vuoi-
quale delle due? Tutte e due.
Mettile sul desktop così poi una mia, una sua.
Ah, ok.
Prova a parlare di nuovo.
make sure that it's working.
Ok, we can try.
Make sure.
Questa è la mia, ok.
Yes.
Ok. Let me try
E
yours.
l'altra era questa.
Rice MLC. Okay, this is yours. This is working.
Yeah.
Okay.
Yeah.
Right.
And yours,
Mine is.
Yeah.
Oh, thank you.
can I take the?
Yeah.
Yes, we
Right?
can eject it.
Thank you so
Okay,
much, lady.
Thank you.
Sì.
Meglio.
Meglio, si vede molto meglio. Ma lei non presenta qua? Questa presentazione è per questa sessione, no? Io non ce l'ho.
Sorry, are you in this session?
I'm not in this session. I reached from Iraq yesterday night, and I arranged with Elise, okay, to
Okay,
put me in
okay.
any session that it's
Okay, okay.
Okay.
oral session.
Okay.
Thank you. Because this is the only oral session here,
Okay.
so if
Okay.
it's possible, I would appreciate if I can.
Sure, of course. But may I ask to start first? May I ask you to start first?
Oh, no problem.
Being the lady in the
No
room?
problem.
Okay, so I
ask
think
you to take some video and photo in this case,
we can
and I will
start.
do it for you. Yeah.
Thank you so much for participating ICCSA conference and this workshop. Let me check, Simone, you are online. Perfect.
Maybe he can talk now.
Yeah. Now he's
okay.
connected to the smartphone, and let me introduce you the first presentation, which is an auto machine learning model.
Sorry.
No problem.
Please come.
No problem. No problem. Hello.
Okay.
Is the title of the presentation is an auto machine learning model to identify abiotic stress associated single nucleotide polymorphosis. Sorry, in rice. And we are very honored to have here the presenter, who is Dr. Suad Usif.
Thank you. I appreciate
And
your introduction.
I think like to keep to have an efficient, let's say, agenda is 15, and then we have a Q&A.
Okay, thank you very much.
And
Hi, everyone.
sorry, you speak to,
To skip to the next and from up.
yeah, down. Okay,
Thank you.
no problem.
Rice auto machine learning, an auto machine learning model to identify abiotic stress associated single nucleotide polymorphism in rice. You know, the rice is very important plant that we can. Sorry. Okay. The contents, I will skip it. Okay. Introduction. The rice. The Oryza sativia, fundamental stable crop, of course, it's a fundamental stable crop, played a sustainable role in agriculture and human nutrition for over half of the world, and we all know this. Important in global food security, because if something happened to it, more than half of the world, they can't do it. Complex genome. And we want to focus on this word, complex genome. Even if it is right, it's a very complex genome architecture. They have only 12 chromosomes, okay? But it's a very complex genome architecture, and we will see it how. And they have many traits, different type of traits. So researchers and breeders face challenges in optimizing rice quality and quantity. For the breeders, of course, they have this face challenges. For the researchers, also, they can use the AI to help this breeder to protect or to optimize the rice quality and the quantity. Okay. I said before, focus on complex genome. So for just this, imagine, this is just rice traits chart, okay? And they have many hundreds of traits. And we will focus today on the abiotic stress trait. What do you mean by abiotic stress state? The state, the stress that is focused on the environment factor. And this is the most important thing we have. Okay? In agriculture, the environment factor. The type of these factors are drought stress, salinity stress, heat stress, cold stress, flooding, nutrition deficiency, and metal toxicity. So this is very important. And from all these, we just focus in one type of the trait. Okay. The problem that we want to solve it here is the single nucleotide polymorphisms. What do you mean by this? In English, and this A, G, C, T, we call it what? Character. But in bioinformatics, we call this base or nucleotide. So the SNR is just single nucleotide. Any change in this, if you see the example, we have this DNA, okay, series or sequences. If I change just one, it will affect, as we see that also on people, not we inheritance all the traits from the parent. There is something called variation in genetic. So it's variation in some traits that we have it. Important understanding we have for this single SNA, NSB, genetic diversity, trait inheritance, and marker assisted selection. Okay. Why it's important? Why SNP is important? It's accelerated trait selection. Pinpointing revealed SNPs speeds up breeding for yield and stress resistance. This is the most important thing. Enable marker-assisted selection. Markers guide breeders to select desired traits more precisely and efficiently. And also, it enhances food security, improved rice variety, address global challenges in nutrition and sustainability. Okay, so we use the AI to solve this problem. It's a مشاكل of صدر. Okay, so we use the machine learning and AI to identify the relevant SNP. Why we want to identify it? Because there are like million SNPs, so we want to identify the most relevant one to enhance to address each type of it and solve it and help the breeders. So the AI uncovers complex relationship in high-dimensional SNP data, because you know it's a high-dimensional SNP. Machine learning models identify key SNPs without manual intervention, of course. Faster discovery of traits, linked markers supports rapid cultivar development. So for this reason, we use the machine learning to identify the SNPs. What's the limitation of the traditional method that other researchers use? Okay, one of them is the high dimensionality data, as we said. Okay, it's good. It's a good chance to Okay, so high dimensional data, classical models struggle with millions of SNP features and limited sample. Overfitting risk, deep model can memorize data without capturing true biological signals, and interpretability issue. Deep learning models, for example, act as a black box, as we all know, so complicating biological validation. So based on these definitions, we now specify the problem statement that we want to solve it. Rice genome has an extremely higher number of SNP markers ranging from hundreds of thousands to millions. It's difficult to use all the SNPs for analysis because of the dimensionality and comparably small sample size found in breeding data sets. Redundant or irrelevant SNP add noise, of course, so decreasing prediction accuracy. Therefore, effective computational technique must be employed to predict the most relevant SNPs. So we use auto machine learning. I don't know your specialist, if you are math or I don't know, but auto machine learning, yeah, it's very important tool, especially for even breeders. Why? Because I don't do anything, a simple step that can anyone do it. I don't to optimize the parameter or select the best algorithm. They did all inside the box of the auto machine learning. I use one of these models, which is T-Pod Auto Machine Learning Framework. We have the data set. The original data set is 6. Okay, I will discuss it later in the other slides. The original data set is 6, and we combine other to compare with other works to see if we can get a better result or not. So we start with the data set preparation, then sequence encoding and data splitting, of course. Then we use more than one type of embedding. You know, the character can manage its inside, so we convert it to numerical. So we use the one-hot encoding, DNA to vector encoding, if you hear about the other document to vector or something like this. And we combine then the two methods, one-hot with DNA. Okay? And then after this, we split the data set for training and testing. And finally, we input this data to the T-pod auto machine learning model to classify and evaluate the matrices that give the best accuracy. Okay, any questions till now? So, the data set, we use a benchmark data set, 8 data sets with 40 or 80. What I mean by 40 and 80 is the length of the sequences of DNA sequences. We have to type 40 and 80. Okay, diverse encoding. I use more than one type of encoding, as I said before, one hot, DNA to vector, and combine both of them. While data scaling, we use the feature normalization to ensure the consistency across the model. Okay, this is the data set that is used. 3 of them is for positive samples, another 3 used for extract negative samples, and then we combine the sequences with length 40 together and the sequences with the length 100 together. Okay, what we have from this model or from this experiment, the result we get a high accuracy. In Rice Auto Machine Learning, we achieve 93.7 accuracy with one hot encoding, because I said we have more than one type of encoding on the combined data set. Other convolution neural network, they just get 61.3. So we enhance the accuracy a lot. Why? Because of the selecting the best parameters and the best features. And automated feature optimization, the T-pod pipelines effectively balance performance and interpretability. Okay. This is performance comparison based on the model architecture, data sets, pre-processing, feature handling, best achieved accuracy, and individual data set performance. What we have from this, the most important thing, here they have the accuracy. This is the nearest research to our research. They use the same data sets and one hot encoding. And we have 93 and we have 0.61. In which type of data set? In the rearrange 100. And finally, individual data set performance, the accuracy, it's just enhanced a little. In our work, it's 62, and in their work is 61. And this is, if you can see the accuracy based on the data set and based on the model that we combined it. So we get here the best accuracy in one hot in combined data sets, and also we get this 62 in the combinations of DNA to vector and one hot encoding. So, what is the advantage of this? It's an automation and scalability. Auto machine learning pipelines reduce manual intervention, of course, and support large data sets, improve interpretability, feature selection mechanism enable better biological insights, and superior accuracy achieves higher accuracy predictive performance than convolutional neural network based framework. So we can conclude that using auto machine learning gives a better accuracy because there are 3 steps inside the auto machine learning that we do it in machine learning. The first thing, they select the hyperparameter using one of the methods. In T-pod, they use a genetic algorithm. They select the best classifier. They try 30 or more classifiers and they select the best classifiers. And at the same time, they tuning the feature selection. They do the feature selection inside the system. They choose the best feature selection method, so they give a better result. Here, they give me the algorithm or the best algorithm, which is XGBoost model. Okay? And apply motive in future work. If you hear about motive, we can apply motive finding algorithms or search that may help in predicting an SPS and finding their exact locations. More encoding technique and larger data sets can be applied to uncover the generality of these findings across various crop traits. And thank you for listening. And I think I will
done. Please stay here for the Q&A.
Yeah, of course.
Let me check hopefully Simone is still there. Simone, tu ci senti?
Sì, vi sento, però io non posso condividere lo smartphone. Sto provando ad accedere ad un altro portatile.
Ok, va bene. Allora, prenditi il tuo tempo, nel frattempo noi andiamo avanti con un'altra presentazione. Va bene?
Sì.
E al massimo la facciamo senza senza condividere lo schermo, nel senso tu ci racconti le slide. Sorry, technical issues.
Okay, do you have any question?
Yeah, if there is any question.
Yeah, there's any question until the technical.
Yeah, we have 5 minutes to discuss more fruitfully.
Okay, I have a question.
Yeah.
At the beginning, you said that the AutoML technique is useful because even people without technical background can use it, you know.
Yeah.
But then I was wondering, usually the genetic data sets are very big.
Yeah.
They have a lot of data, and if they are big for even small data in the genetic, right?
Yeah.
Am I correct? Okay.
You mean the sequences of DNA?
Yeah, I mean, even sequencing a little organism takes a lot of data.
Of course.
Am I correct?
Yeah.
Are there any techniques that can be applied maybe to pre-process this data in a way that can make it more efficient to store, for example?
Right. We don't need to pre-process. If you check for researchers, sometimes they use they create the data. Just it's not a real data. But for real data, really, it's a very. This is the one that I use. It's real data.
Okay.
It's for rice, and it just have 12 chromosomes. Okay. And the DNA sequence that we choose is 140.
Okay.
So we cut it from the DNA. We just like take a part of it. Yeah, of course, because we can't take. And this part inside it, because I use classification.
Okay.
So you know that there is a label. True?
Yes.
So inside this sequences, there is either an SP or not.
Okay.
So if you have SNP, which is the positive, it will be okay. We will identify these relevant SNP.
Okay, so you do it in little sequences, and that way you can simplify the problem.
Of course.
Okay. Thank you. Thank you.
Another question, please. Dr. Willis, yeah.
I can add something. The teapot, when use genetic algorithm, it's only using it for small parts of data just to initialize the parameters. It's not actually using it or applies on the whole data. It's just for parameter initialization and setting.
Okay.
And then after setting all the parameters needed,
You can use the
then
base.
they will apply these parameters and use it and start to do the classification, but without using the genetic. Genetic is used only for optimizing and
Yes,
specifying.
I think he asked for the chromosome link, for the DNA sequence link, not the genetic algorithm.
Yeah.
For the sequence, because it's very, very long.
Very
No.
big.
Yeah, very, very big, so we can't, yeah.
And
What
I
feature?
Features in what?
Within the chromosome.
On this chromosome, here it's 12.
80.
12?
12,
yeah.
It's not a big one.
Not a big one. I said it's in the rice, it's not a big one.
Actually, the chromosome consists of a lot of genes,
Yes.
and there is only 12 genes.
So it's not in rice, but I think you're thinking another thing. For example, human.
Yeah, I was thinking
Yeah,
maybe
that's
about
very
that.
different.
Yes.
Yeah, it's a very different situation.
Yeah.
So this help the breeding.
Thank you.
Another question, please.
I have a question and a comment. So thank you.
Thank you for
I really appreciate you jumping the conference. I can see the
I will
urgency.
do it always, really. I
Yeah.
did it always. The same thing in London. They close the door and I come and say, I must give a presentation. Open the door, please.
You are very motivated to introduce the research topic you are following, and I can feel it. So first comment, thank you, because I think nowadays there is a crisis related to rice. At least in Japan, I read some news, but
Especially,
it's,
yeah.
given the uncertainty of the global crisis. I think this kind
And
of
they use
research-
it a lot now.
Yeah,
You
yeah.
know, in
And then
agriculture.
the,
Yeah.
the question I had, so yes, 2 days ago, with Federico, who is a colleague of mine, we were having this chat. His brother is doing a research about modeling the metabolic process of the human body. So I don't know if TOPOP is the
I
algorithm.
think it's quite similar.
Quite similar
Like
approach.
It's more than one. It's H2O on top, but
Yeah.
a lot of auto machine learning that it's helped just to know or to choose as Dr. Vino said, is to choose the best parameter. So they use it for initialization.
Yeah,
Let's say like this, and then, for example, here I know that it's XGBoost. Maybe I take this and do another thing on it, or compare it with the default parameter.
Yeah.
You can do a lot of things.
Because the question is difficult question also to review. I would say this workshop today is about the experience of the user in the city, in the urban settlement. And in the introduction of the talk, you mentioned 8-9 stressors for RISE.
Yeah.
So for
That is yes. You mean?
the stress
Yeah.
and I was thinking we work a lot on thermal comfort, which in summer season everyone
Yeah.
recognizes is
Yeah.
the problem. So maybe
Of course,
if you could,
of course,
if you could
population.
help, let's say,
Of
the
course,
community
of
of
course.
ICCA for developing,
Of course.
because we are
So
modeling
just
the
I'll give my
pathophysiological-
email, and I know it's.
Yeah.
I know. Yeah. With a pleasure.
Thank you. Thank
And
you so
I'll
much.
jump again. Thank you very much.
You want to
Take
take
a
a picture
photo like
together?
this.
Do you want the cover page?
No,
Or the-
Yeah, I wanted to-
Yeah, maybe the cover page is.
Mi sentite adesso?
Ciao Simone, sì, ti sentiamo
Ok.
forte e chiaro.
Bene, I apologize for the delay.
Okay.
Okay.
Can we do together?
Thank you, of course.
No, not on the title, on the side though. Yes.
Così,
They want to separate us. Yeah.
separate. Così.
Yeah, they want this.
Sorry, I'm not so. Okay.
Okay,
Thank you
no
so
problem.
much.
Thank you. Just the last photo. This is for the university.
Yeah, no, I know.
Thank you. Thank you. very
Thank you.
much. Thank you.
Ciao Carmen. Ok, a te Jacopo scoccia chiudere perché loro sono tutti online, secondo me almeno. So I think we can introduce you the second presentation of the day, and very happy to see Carmen online. So the paper is titled, let me development of a walkability index in support of urban planning decision making. Carmen is an associate professor at the University Federico II di Napoli, and she will introduce us the topic. Carmen, can you share your screen?
Yes. Hi, everybody. Thanks for the introduction, Andrea. I'm sharing my full screen now.
Yep.
Here it is.
Thank you.
Okay.
Okay.
I think it's working. Okay.
Yep.
Okay. So good morning, everyone. Thanks for letting me presenting online this work, which is titled Development of a Walkability Index in Support of Urban Planning and Decision Makings. I contributed to with my colleagues Gerardo Carpentieri and Andres Davide Maglione. Our work falls within the topics developed at TEMALab, which stands for Laboratory of Land Use, Mobility and Environment of the Department of Civil Building and Environmental Engineering at the University of Naples, Federico II. And this is a presentation, a framework where I'm going to present you today, starting from the background and objective. Through literature review, I'll guide you through the results of the methodology we framed for this purpose. And finally, the conclusions. We live nowadays in cities that are struggling with urbanization and also with the issue, with the concern of turning to more sustainable development for the cities of today and of the near future. But cities also struggle to fight with the car dependency legacy that actually led to air pollution, chronic disease, lack of planning in distributing services within urban environment. While walkability has been recognized also by literature review as um, a proved benefit for the sustainable development of the cities, at the same time, still we actually assist to a lack of investment in such field. And one of the reasons may be that still, like the measurement, the assessment methods that have been developed in scientific review, in scientific literature actually, they struggle to be translated into effective policy making support tool. So the purpose of our study was to support decision-making processes, implementing intervention that improve walkability in urban areas, especially at the neighborhood scale, by developing a walkability measure in a GIS environment that takes into account two main elements. On one side, walkability environment of the urban areas, and on the other side, on the other hand, the availability of services within neighborhoods. We started from a systematic literature review of literature. So we actually developed a literature review that was.
Ragazzi, aspettiamo. Let's check if.
Um,
Sorry about.
is everything okay?
Yeah. I mean, there is a slightly poor connection on our side,
Oh,
so it happened
okay.
already once, but it's clear. The narrative is clear. Please continue.
Okay, thank you. Oh, in case there are any problem, just text me
Yeah.
anyway. So we started actually looking at the features that actually contribute to measure and to assess workability in urban environment, especially from the point of view of the features of urban environment. And what comes clear to reviewing literature is that in recent decades, workability within urban environment has actually reached within so many features, starting from the 3Ds developed by Cerbero to the 7Cs actually developed in more recent years. So we can distilled actually four main domains that can be seen as four main components of factors, urban factors influencing walkability. We find them also in more recent works as one of Blecic in 2021 as four main components. Safety and may mean as the pedestrian exposure to risks caused by conflict to with other types of mobility, but also includes the sense of security conveyed by the urban environment. Then comfort, which is meant, means the practicability of the use of urban space. This includes physical factors that allow or also restrict movement within urban environment. Thirdly, attractiveness is another feature that can allow people to perceive opportunities and services which are accessible by walking distance, and pleasantness that can be summed up as the perception of the urban environment as beautiful. On the other hand, what we were looking to was actually assessing how this feature can be measured. In literature review, many methods have been developed. They go from surveys, but also direct control tools aimed at measure the walkability environment. And GIS tools actually represent a way to streamline the process and better manage and also mix these methods together in order to have both quantitative measures, but also combine them with qualitative measure aimed at perceiving and actually getting the perception of the features made by who walk that urban environment. On the other hand, walkability has become a topic mainly connected to also proximity services, is now on the topic of the urban literature, the 15 and the 20-minute city. And so the proximity to essential services is one of the other traits that have been considered when developing walkability assessment in literature review. So we also reviewed literature in order to take into account how cities actually develop the walkability measured, considering different kind of services and proximity services, which range from mobility to urban space, from education to general and food retail, from health and leisure activities. So to sum up some conclusion from this phase, actually, we realized that there is a growing interest in studying the ever-changing factors that have an incidence, have an impact on walkability. The concept of walkability, unlike that of accessibility, which focuses on the possibilities and opportunities of interaction with the urban environment, must also take into account the interaction within the urban spaces and mobility. Within this scenario, the GIS tools present themselves as an opportunity to combine these elements, the features, and so to increase the level of resolutions of the analysis themselves. Given these premises, we developed a methodology, which is divided into five main steps. The first one concerns the identification of the system of open spaces, because we realized when working with the topic, there are actually not only pedestrian streets, but also the combined element, both vehicular and pedestrian elements can be seen as a walkable environment. And so we decided to develop a network that takes into account also the system of open spaces in order to gather all spaces that can be walked by people, so can be used by foot. The second phase concerned the data gathering. On one side, to create a walkability index that was referred to each segment of the network and took into account attractiveness, pleasantness, comfort, and safety, and the variables defining these main components. And finally, proximity services as another issue to be considered when dealing with the pedestrian accessibility score. So through data analysis, we measured walkability index that we used as a weight to consider and to weight the accessibility opportunities within origin and destinations. And finally, we try to identify priority areas of intervention through the selection of type of intervention. So this is to sum up the main topic. So we started with identification of the system of open spaces in order to take into account and to give a different weight to different elements of the network, taking into account also crosswork, mixed surfaces, and also only pedestrian surface, only dedicated to them. So starting from the OpenStreetMap network, we adjusted also topographically this network in order to take into account all these elements. Then we looked into the main features of walkability, so safety, comfort, attractiveness, and pleasantness, in order to define variable aimed to measure them, and also give them a range that was somehow coded and defined by law or guidelines or also by literature. These are the examples from the safety and comfort variables. So they go from, in safety, the distance from light sources, to, in terms of comfort, to the presence of trees or the presence of obstacles on the road. All these variables were also chosen not only based on the, of course, the ground-based significance in literature, but also on the possibility of getting these data as open data from Google Street View. From the attractiveness and pleasantness point of view, we chose absence of squares, park, or exclusively pedestrian spaces, or in terms of pleasantness, the level of cleanness of the areas, or the combination, the conflict due to vehicles parked on the edge of the street. Each of the variable and each of the feature were then weighted through a survey. We find Kij, sorry, that is referred to each of the variables I listed before, which contributed to weighting each of the factor, so of safety, comfort, attractiveness, and pleasantness. This is the formula of the walkability index, which is meant as a combination, linear combination of the variables listed previously earlier with their component, with their significant weight. This index actually was used as a weight to compute the pedestrian accessibility score, which is a countermeasure of accessibility that takes into account the number of available resources given the origin, N, which is the residential origin of jewelers in a certain neighborhoods.
Carmen, sorry, you were frozen
Oh.
while introducing the formula. So if you can
Okay.
jump back one slide,
Okay.
it would be very
Okay.
useful, I think, for the audience.
Okay. Thank you, Andrea. So I was presenting here the walkability index, which is meant as an index for each segment of the network. Each link is meant as a linear combination of the variables I listed earlier, referred to safety, comfort, attractiveness, and pleasantness. Each of them is weighted to K weights that represent the weight of each element perceived by users while walking the neighborhood. This formula used, so the walkability index is actually a weight within the pedestrian accessibility score, which is meant as a gravity contour based accessibility tool, because the formula is meant to be a sum of available resources, available opportunities within a certain contour given an origin, which is the residence of jewelers within a certain neighborhood. So opportunities are counted given their presence within a threshold. It goes from the origin destination within 15 minutes of distance, but this travel time, so TMN, which goes from the origin N to destination M, is actually not only a combination of how far people can walk from their origin, but the speed they can walk through is weighted by the walkability index score. So that's why the pedestrian accessibility score is a combination of both an accessibility measure and also walkability measure. So it aims to contribute to combine both these two dimensions. The pedestrian accessibility scores was then divided into categories, so the final results, in order to get priority areas intervention, so combining not only the presence of services, but also take into account where actually people live in order to identify areas of interventions. The methodology was applied to neighborhoods in the city of Naples, Ponticelli, which is a neighborhood located in the eastern side of the city. Its population is more than 50,000 people, with a surface that actually covers more than 9 square kilometers. This is the sum of the network of the Ponticelli network, which is made of 1,458 segments, so links. So the graph of the network is made of this amount of links of segment. The 63% of them represent mainly pedestrian surfaces, mainly pavements. 27% of them represent crosswalks, while 10% represent by mixed surfaces, where actually mixed pedestrian flows actually can meet a different kind of flows as vehicular flows. This is the results for the WI, so the walkability score, after a survey made to the population. Sorry, you may see the picture not in high resolution, but represent the results of the survey in order to compute the K, so the weight of each of the feature, aimed at measuring walkability, ranging from safety to pleasantness. Then we measured, of course, each of the each of the indicator through Google Street View maps. We were able to assign to each of these variables a value ranging from 0 to 1. This is an example screenshot from Viale Margherita, which is one of the network. So we were able to identify presence of trees, the presence of residential buildings, parking at the edge of the road. So we were able actually to measure each of these variables, contributing to defining the safety, pleasantness, comfort, and attractiveness of each link of the road through Google Imaginaries. And we were able so to compute a walkability index that, as I mentioned earlier, was a weight that we use also to compute finally the pedestrian accessibility score. What actually is clear is that mainly the walkability index falls in a poor and medium, I'd say, walkability index. So especially this area of the city, is the northern part, which is a more recent developed area, planned developed area, suffers a poorer walkability issue. Then we computed the pedestrian accessibility score, starting from the origins. With
Carmen,
origins,
sorry, I need to ask you to speed up a bit.
Okay. I'll go
concluding the
further to the
presentation.
results. Okay. So we defined the accessibility services we want to compute, and we finally led to the results, which were the combination, as I mentioned, of the walkability index and of the accessibility perceived within areas. Actually, these results show that poor accessibility, pedestrian accessibility, actually not only overlaps with a poorer distribution, a poorer availability of services, but it also overlaps with actually higher unplanned, I would say, patterns of the urban environment. The final stage was actually to combine these results with where people live. So we made this intermediate stage that actually led us to identify high priority areas, which are not only places with a poorer accessibility, but also where most of the people lived. This condition was actually needed because we had to not only identify priority areas, but also to understand which will be the dominant for intervention, which actually were these area here highlighted. Just to conclude and to present a few conclusions, from the literature review, we understand the need for a systematic and integrated approach to deal with these issues, so with walkability and accessibility to services. The results need to be easy to communicate to stakeholders, and GIS can actually streamline the process and increase the level of resolution for the analysis. The methodology we try to implement, and that still has many room, it has much room actually for improvement to some of the limitation we highlighted also in our proceeding, is the possibility, though, to identify priority intervention on the urban environment. But actually, the main trait of the methodology is the aim to combine both the distance of proximity services, but also the walkability, the quality of the urban environment through perceived quality and walkability. These are a few limits we actually want to work on in order to improve the methodology and to next steps expand the validation across a broader sample of open spaces areas and also to apply it to different neighborhoods, engage stakeholders, and also apply the methodology in different urban contexts to test its transferability and robustness. I'm sorry, I hope I didn't got too late.
No problem, Carmen. I think it's a very, let's say, informal conversation, as ICCSA is always. So I truly appreciate your presentation, but I would like to give the audience the opportunity to push you a question first, if
Okay.
any. Jacob, have a question?
And I have a question and a comment that might be helpful, I think. First of all, thank you for the presentation. It was very interesting. And we are always looking for data because we're working with this kind of stuff, and we're trying to integrate data into our data set. I'll explain later what we're doing. And basically, we're working in the area of Milan, and but we're doing a very similar thing. We need the walkability index. But one of our goals, for example, is making walking in the neighborhood more accessible for people with disabilities.
Yeah.
Have you considered adding specific markers for disabled people, maybe for accessible road network infrastructure, maybe ramps, etc.?
Yeah, actually, thank you for your question. That actually highlights one of the further development of the research, because for this case study, actually, we started as a streamline, and we also to like prove the methodology, but of course introducing these kind of features will be extremely interesting also from the as you mentioned, from the collection of data from the urban environment, so from Google imageries and stuff. But I think it would be super interesting also to getting the data from people, so getting the possibility also to go through the perceived safety and comfort, attractiveness and pleasantness, especially of people with limited mobility opportunities, disabled, but I'm also thinking about elderly people, for instance. That would be super interesting, and maybe the walkability index will even lead to more insightful results also in terms of intervention, like a range of intervention. Not sure if I replied correctly because I had some issues listening your but I mean the idea is to
And there's another thing I wanted to say. You use the OpenStreetMap dataset, right?
right.
Right. And how did you choose the segments? Did you filter out all the roads, for example?
Yeah, actually, it was throughout the many elements. So all the 100 and 500, 1,500 segments, links were actually investigated in order to collect data from them. This is one element actually that has plenty of room for discussion, also due to the use of AI-based data collection that can also improve not only the quality of data that has been collected, but also the kind of data collected. For now, we were into like collecting data that were kind of ranging from 0 to 1, and also we actually that of course worked for our case study, but we recognize that it can be also there's room for improvement also in that and further development. Also still using big data, and also include maybe AI based tools to collect data and also on a continuous scale rather than getting into discrete level.
Okay. But did you notice a lack of crosswalks, for example?
Sorry?
Did you notice a lack of crosswalks?
Oh,
Maybe. Sorry, go on.
no, sorry, finish first.
No.
So the lack of crosswalk, yeah, actually, but it is something we had to add to our network. So we were going through Google Imaginaries also to implement crosswalks, where of course they were. So the network actually that we used in ArcGIS network analyst models takes into account crosswalks also as a link, of course, for the workable environment.
In some cases, we found out that the crosswalks are not marked as pedestrian roads, but as tags into the actual road network.
Yeah.
We go into the road links and the tags and look at the tags and extract the fact that there is a crosswalk from the tag.
Yeah.
I don't know.
Yeah, actually it was a mix of both combinations. So we started from the OpenStreetMaps, but also validated it. We were able to do it because of the network, because of it was limited to one neighborhood, of course. So we went through like validation in both direction, I'd say, because not every, of course, crosswalk was marked. So we actually did tried to do our best to collect them also. So.
And did you contribute back to OpenStreetMap then?
Yeah, actually we weren't able to like add them still actually, but yeah, maybe that would be a great idea, I'd say, to contribute back to OpenStreetMap and map the crosswalk. That would be a further necessary step to be done.
Thank you very much.
Thank you, Carol.
Thank you.
A big applause to you.
Your pleasure.
And Jacob, I think you can jump on the stage for presenting your contribution. So let me.
I mute myself, but I'm here.
Okay, ciao, Carol. Okay, so let me share the screen. Do you see the screen, right? It's shared online.
Are you talking with me?
Someone is sharing the screen though.
Sorry?
Maybe we can let Simone is sharing the screen.
Simone,
we can let Simone do his presentation or do it after?
no, Simone, sorry, I do prefer to have one from remote and one from in-person.
Oh, okay, sorry. I thought there were 3 speakers. That's why. Okay, sure.
Yeah, no, we have a 4th one, which is the.
Okay, sorry, I didn't know that. Okay, great.
Ok, questa qui. Ok, aspetta che ricondivido io lo schermo. Sì.
Sorry, we need to.
Sopra
ok.
sotto.
Okay,
sopra le frecce su e giù dovresti.
Ok, sopra e indietro.
È un po'.
Ok.
15 plus Q&A. So 15.
No, that's okay. Thank you all for being here. I'm Jacopo Mantagliati. I'm a research fellow at the University of Milano Bicocca. And for the past year, I've been working with Professors Leporati and Micucci, my supervisors, on a platform for personalized navigation in urban environments. Actually, this is part of a larger project, which is financed by the European Union. And we're working on 2 completely different navigation solutions, one for outdoor environments and one for indoor environments. I won't be talking about the indoor solution today. We'll only focus on the outdoor application. And the idea started as an application. Then we attached the dashboard for viewing the data that we collected for the application. And then we realized that we could abstract the features that would be both for the application and for the dashboard, and create a framework that can be used to build a customized solution adapted to your whatever needs. And we call it Wizard, which is a combination of words. Maybe it's meant to convey that the main aspects of the framework are to support visualization, routing, and data analysis. These are, as I just said, the core concepts of our framework. We have a personalized routing component, data aggregation component, and a visualization and analysis component. The personalized routing and data aggregation components are fundamental for covering the use case of end users that need to have an application on their phone to go maybe from one place to another. And you might say, yeah, but there's already a lot of solutions that do that. For example, there's Google Maps. But we will see how our solution differs from Google Maps in this regard. The other 2 components, which are data aggregation is linked, but visualization and analysis is not so useful for end users because they don't need to interact with the data. Maybe they're curious and they want to see the data, but maybe it's not even possible to share the data with the end users because of maybe how it's been collected and everything. But it might be useful for another user, which is the knowledge integrator. That is the person that creates the data set. And they maybe need to do further analysis on their data. They just want to visualize it because they have a rich data set. And it's good to have tools to visualize and analyze the data. This is the architecture of the framework. We will start with a data provisioning system, which is basically a combination of tools that we developed to take custom data sets and an OpenStreetMap dump from a bounding box, merge it together, apply several pre-processing steps. We will talk about the pre-processing pipeline in detail later, and add it to a database, which is the data access component. The database is PostgreSQL. We use a combination of PostGIS and PG routing and custom functions to do all of our processing. And then we built a RESTful API. Actually, it's based on JavaScript, but it doesn't need to be based on that. It's just a specific implementation of a generic API that we defined. And then we can attach different front-end applications to this API to interact with the database. The end users will interact with the front-end applications, and technically also the knowledge integrator can interact with the front-end application if we want to build a dashboard. For the system that we developed for the paper we presented here at ICCSA, we just focused on the end user use case. We have another paper in the works that will focus on the knowledge integrator using the dashboard use case. Let's move on to personalized routing. Routing system, as I said, they're optimized for hard problems, like maybe distance or time. I have to get to the airport in the fastest possible way or the shortest possible route. But really, in a urban setting, when maybe we focus on the campus of our university, you don't need to be fast, maybe. Yeah, you might need to be fast. Maybe you're late for your lesson, but you don't actually need that. Maybe you're just taking a leisurely walk, or you have some time because you want to go to a restaurant, you want to go to grab some food between your lessons, but you don't want to take the fast route. You want to take the scenic route. Maybe you want to go through a park. You want to be with your friends. So you don't need the fastest route. You don't need to cut between the busy areas of the city. You just want to take a leisurely walk. And with our solution, you can do that. Of course, this might also be useful for other demographics. For example, people with impairments, vulnerable categories, kids, the elderly, as it's already been said when we discussed the previous presentation. And there are also other preferences. There might be users that want to cycle, users that want to rent a vehicle. And there's a lot of vehicle rental services in the city, and our solution supports that. To do this, as I already said, we need diverse data sources, but we also need customizable cost functions, because if you need to optimize for different use cases and based on the preferences of the user, you need to let the user express the preferences and that customize your cost function to actually reflect the needs of the user, the preferences that they selected in the application. Okay. This is a dashboard of the application we developed. That's a pilot application. Not specifically tied to the framework, but it's actually what we use to develop the framework. So it's useful as a demonstrational tool. And you can see here that we planned the route from the train station to a building of the university, a main building of our university. And for example, in this case, the user didn't select any specific routing option. But here you can select to avoid air pollution, to prefer the green routes, to prefer low-speed roads, so maybe where the safety is higher, to avoid traffic, if you're mobility impaired, a lot of things. You can also choose a vehicle of your preference. We have a selection of vehicles. And then you can activate vehicle sharing. If you activate vehicle sharing, there's another system that is called LUMIs, last user mobility interchanges. There are places where you can rent a vehicle or leave a vehicle you rent. So the application will route you to the nearest LUMI, then to the other LUMI with the vehicle of your choice, and then the other LUMI will be the nearest to your destination, and then you will continue on foot after you left the vehicle. Of course, we need to visualize these features on the map. So we have built an overlay system, and you use to visualize POIs, points of interest. For example, here we can see the building of the university, which is a point of interest, of course, for a use case. But you can also visualize the LUMIs, where you can take the rental vehicles or the train station, for example. So in mobility interchanges in general. Another important thing, as I was saying, when you rent a vehicle, you need to enable the router to support multimodal routing. because the rules for routing on foot are different from the rules when routing on bicycle, for example. You cannot use the same infrastructure in some cases, and you can in other cases. So it's a bit of a complicated matter. Actually, this is a demonstration of the intricacies of multimodal routing. For example, this is a route that was suggested to a user that wanted to rent a bike. You can see here in blue, these are cycling roads, and in orange, you can see a cycling path. So here, the router will make you take the bicycle, and then it will suggest you get off the bicycle, because to continue on to the cycling path, this is a road, you can freely cycle here, there is a connecting path that you cannot cycle on. This is forbidden, because it's a pedestrian road, you cannot go on there with the bicycle. Of course, people do it all the time, but that's not the point of the application. We have to follow the constraint of the road network, and to do that, we needed a lot of pre-processing of the data. We use the OpenStreetMap data. I have a rundown of the data sets at the end if you want. We use OpenStreetMap as a data set, and we have to pre-process it heavily to support this kind of multimodal scenarios. Onto the data aggregation step. Having the route network graph is not enough for our solution, because of course you need to personalize the route based on the preferences of the user. So you need contextually relevant information about the infrastructure. For example, greenness, tree coverage, which are similar metrics but different. The greenness is when maybe a road goes through a park, and the park is defined on the graph. So you maybe interpolate the graph with the parks, and you find the routes that best through them. Tree coverage, traffic, external data sets. Equality, standard data set. Walkability indices, as were explained in the last presentation. Very, very useful in this case. And we always try to integrate that kind of data because it's very useful, very granular, and can help a lot in routing efficiently. Rental vehicles as already a point of interest, as I've already said. And we also need, of course, lots of data regarding the road network because it's useful for multimodal transport. Also, for example, surface quality is important because you cannot use an e-scooter on an unpaved road because you won't be able to, While a bike can go there without problems. So the cost functions are really intricate in this kind of case. This is the pre-processing pipeline that we use at a high level. We define a bounding box. We use OSM convert, which is a command line tool that is able to automatically take the OSM the information from OSM and build a dump. We then import the dump using a patch version of OSM to PG routing. We patch it so we can keep more information because we actually want sometimes the original tool couldn't give us. So we made a patch, a couple lines of code. Then we have additional data sources. Can be different things, CSV files, for example. Functions and procedures, which I'll explain later, but they're very useful in our use case. And they're written in the SQL language and can be imported directly into the database. Then we have which are 2D images with a single channel, and overlay them onto the road network. We choose the nearest points in the graph, assign the value to the nearest points, then average them and apply them to the segment. We use pSQL, which is SQL's command line tool, to import them into the database. So basically, you have map retrieval step, graph building step. As long as you've done this, you build the graph, and then we have the data augmentation step. All of this is additional data that gets imported into the dataset in other tables, and that have IDs that can be used to join the data with the graph and obtain what we need. Onto the visualization and analysis component. We have a lot of data. Why shouldn't we let people that want to build the dataset interact with it? The framework allows for custom visualization. We have support for filters. For example, you could try to filter only for cycling roads if you only want to see data related to that. We have functions and procedures, which are useful for augmenting the visualization system and also the dataset. Functions are more of a live thing. You can use a function, you can define a function and use a function live to create maybe a new visualization directly in the user interface. And you can use a procedure to do this while you're building the graph. So in the graph building step, in the data augmentation step, you can use a procedure to pre-compute some metrics that they're not available to you, but they're maybe computationally intensive. So you do it offline, so you don't have to do it online later, and you don't have to wait. We're trading basically we're trading this space for efficiency. The goal of this is, we also have coloring for class, of course, because if you want to see the data, it can be great. Of course, the goal of this is having targeted analysis. For example, we can study the placement of useful road features. I want to add a bus stop, I want to add a water fountain, I want to add a shade, for example. We could integrate a lot of data. We were talking about integrating, for example, tree coverage data could be useful because we could use it in the summer to define where the paths with the most sunlight. So maybe you have to add covers for people walking. Commercial applications. You could decide that you and then, of course, it's useful for the academy and research projects. You can visualize the data, interact with it. It's always useful for us. This is an example of a visualization. This is traffic. Very simple visualization. Most basic thing we can do. This was filtered for the roads, so we're only visualizing the road network here. No crosswalks, no cycling paths, etc. Because it doesn't make sense to visualize traffic on those segments, which don't even have that data. And so we filtered it, and then we have applied a coloring scheme that is compatible with the traffic data we have. We have, in this case, 5 classes for traffic. There is a completely blocked road. Maybe there's an accident. Then we have lots of traffic, bit less traffic, also a bit less traffic, no traffic. This is a synthetic data set that we use for the visualization. We've tried to integrate, and we succeeded actually. The TomTom, the traffic datasets, and we also built a layer component that can allow you to visualize time series data. So you can choose a specific price if you have a lot of, for example, traffic snapshots for different time of the day. You can visualize just one of those. Then we have more complex visualization strategies. For example, this is air pollution view, which uses different weights for the lines and uses a semi-transparent scheme with a lot more classes. So we can visualize it more organically. And this is a very basic example instead of visualization of just the pedestrian network, like no data. You can also decide to do this. I just want to see where the walkable paths are. At the end, we have the functions and the procedure. I already talked about them, but basically, again, the function is useful for real-time computation, while the procedure is useful for offline computation. You can add the result of the procedure to the datasets offline, and the function is just add to the visualization. You cannot save it back to the books. Thank you. I'm done. Any questions?
Thank you, Jacopo. Truly good presentation, and also, I have lots of questions, but I would like to give first to you all the possibility to push for any comment or feedback. Also, Simone, Carmen, online, if you have any. We are running late the workshop. We have not so much time, but if you have at least one question, it would be great to discuss all together. Aspetta, non usare il telecomando che così riesco a muovere il mouse. Ci sentite ancora? Sì. Allora, facciamo così, magari saltiamo. We can jump on the presentation of Simone and then wrap up with a Q&A session all together.
No problem. Okay. Thank you.
Thank you, Simone. Thank you, Jacopo. Ok, Simone, ci siamo. Condividi pure il tuo schermo.
Yeah, sure. Can you see my slides?
Yes.
Okay.
Yeah. Okay, feel free to start.
Okay, thank you very much. Thank you very much for being here. So my talk will be a little bit different from the previous one. I'm an optimization guy, so I work a lot on the numerical optimization side. And today I'm presenting a joint work with Stefania Bellavia and Mattia Silei from the University of Firenze. Mattia is the PhD student of Stefania working there. So here you have the main references for this talk. The first one is, of course, the conference proceeding for this conference, and the other one is the follow-up paper that we are about to submit. So here I'm going to focus on a mathematical problem, which is the problem of a fine rank minimization problem. So here we are looking among all possible matrices of a certain dimension, so we have a certain number of rows and columns. We are looking at the matrix that has minimum rank above all matrices that satisfy a set of linear constraints, where A is the coefficient matrix and B is the vector of the data. So of course this is a very general abstract problem which find several applications in many different fields. The one that we are focusing in this paper is image reconstruction. So the idea that we can recover an image which of which we know only a certain percentage of pixels. So sparse image reconstruction. Okay, so this is a very difficult problem. This is a non-convex optimization problem due to the presence of the rank function, and it is an NPR problem. So of course, literature is full of possible approaches to deal with this non-convexity. Of course, we can relax the problem and use, for instance, replace the rank function with convex relaxations such as the nuclear norm. But here we are interested in reformulating the problem as a feasibility problem. What do I mean by feasibility problem? Where I think that you know in advance the rank, the minimum rank of the matrix that you want to find, or say a reasonable estimate of this rank. And then the problem, if you have this rank R, is equivalent to find a matrix which belongs to the intersection of two different sets. The set CA is the set of the linear constraints, and CR is the set of all matrices whose rank is smaller or equal to R. And so one very basic idea to solve this problem, to find a matrix that belongs to the intersection of two sets, is to use the so-called alternating projection method. So the idea is to basically alternatively project onto the two sets CA and CR. Also because the projection operators onto these two sets are or should be easy to compute. In particular, if you want to project onto a linear set, then we know that the projection here has this formula. And so, of course, if you can find the inverse of A times A transpose, then you can actually project onto CA. There are many contexts where this projection is really easy to compute. And also projecting onto the rank level set is quite easy. In particular, this can be done by considering the singular value decomposition, the matrix X, which you can see here. If you block partition the matrix sigma by isolating the first R singular values, and then partitioning U and V accordingly, then we know from a theorem, which is called Icard-Young theorem, that the projection of X onto the set is given by the SVD of X truncated to the largest R singular values, meaning that the projected point has this form here, where the first R singular values are involved. And so, of course, computing the singular values of a matrix is in general a very costly problem. So, of course, we can do that in theory, but then in practice, we need to somehow approximate this projection. Okay, so here I'm reporting the problem more in general. So I now use the notation AB to denote the two sets on which I'm projecting. So A, say, is replacing the linear set CA, and B is replacing the non-convex set CR. And so the problem here is to look for a point in intersection of the two sets. And the alternating projection method is as follows. We start from an initial point belonging to the set B, and then we project first on the set A, obtaining the point xk plus 1, and then we take this point and we project it onto the other set B. This is a very classical method, which was, of course, devised in the 50s, so a very classical method. And so here I'm just giving some information about the convergence of this method. So here, by global convergence, I mean that the sequence of the points that I'm generating with the method is converging to a point of intersection for any initial guess. So for any initial guess, I can converge. I'm converging to a point in intersection. So this is true only when A and B are convex. But in the non-convex case, which is the case of affine rank minimization problems, then we need more assumption on A and B, and we can only hope for local convergence. So the initial guess should be chosen properly in order to have the convergence of the algorithm. So here I'm giving a very theoretical result, but I want to focus on the hypothesis. So here I'm asking that the two sets intersect in a proper manner, which means that they intersect separably. And in the next slide, I'm reporting depiction of this condition. So think of having 4 points A, B, A plus, A, B plus, and B is a projection of A plus is a projection of B, A plus is a projection of A plus. And you consider the angle between these two vectors over here. And so what I'm saying with this condition, separable intersection, is that this angle alpha is going, of course, to 0, but this angle shouldn't go to 0 too fast. So in particular, it shouldn't go faster to 0 than the distance, than the length of the vector up A plus minus B plus. Okay, so this angle shouldn't go too fast to 0. And the other assumption is that B is Prox regular, so we are assuming that the projection is unique locally to each point of the set. So if we have this assumption, we have the convergence of the algorithm only locally. Okay, so here in this paper, we are focusing our attention on a variant of this algorithm, in which we introduce regularization. In particular, we have two sequences of parameters, lambda k and mu k, which belong to an interval t minus t plus. And here we are considering this modified algorithm that you see here, where here I'm projecting not xk, not yk, and not xk plus 1, but instead I'm projecting two weighted points. I'm considering the mean between xk and yk, and the mean between yk, xk plus 1, where you can see here you have the weights depending on lambda and mu. So here I've reported again another graphical depiction. So if I have the points x0, y0, I consider a point which belongs to the segment that connects the 2 points x0 and y0, and I project this point onto the set A, obtaining the point x1. And then I do the same for the point y0, x1. So I consider a point which just lies in this segment here, and I project it on the set B. And I repeat the procedure indefinitely. So this is called, I'm calling this algorithm RAPM, regularized alternative projection method. And so what is interesting of this, the interest in this method is that we can ensure the global convergence of the sequence of the iterates. So differently from APM, we can ensure that the sequence converges always to a point which is a stationary point of this function that you see here. So here you have the distance between 2 points x and y to the power 2, and here you have the constraints on x and y. So basically, APM is an alternating minimization method on this function here. And if you consider the regularized version of the method, you can prove that the iterates are convergent to a critical point of this function here. So reformulating the method as an optimization method, you can prove this, and which is nice with respect to APM. And you have a very technical assumption on L. L should satisfy a property which is called the critical Gaussian property. I'm not going into the detail of this property, so I'm skipping it now. And you can obtain also some convergence rates for the method. And finally, I want to give some details on our proposal. The regularized method that I showed you before was proposed 15 years ago. So here in our paper, we are proposing a new variant of this scheme where we are considering inexact projection. So as I said, of course, in our fine rank minimization problem, we know how to compute the projection. But the problem is that this projection operator here, in practice, will be approximated. And in particular, there will be an algorithm, usually a Langsos algorithm based on which needs to be stopped. So you need an iterative procedure with a certain stopping criteria. You need to stop the iterations properly to compute properly the function. So here we want to propose, in our paper, we propose an inexact version of the RAPM algorithm, where we define the inexactness criteria in a very rigorous manner, and then we also provide a practical procedure in order to comply with the inexactness criteria. And so our algorithm is simply the same as RAPM, where yk plus 1 would be an approximation of the projected point onto the set B. So we need to compute exactly the projection onto A, and we compute inexactly the second projection. So this is our scheme, and this is the depiction of the algorithm here. So basically, now at each iteration, we are again projecting on B and A. We are projecting exactly on A, but inexactly on B. So this cone that you see here is the admissible, the feasible cone where we can find an inexact projection. And the size of this cone will be restricting as far along the iteration. So as the iteration proceeds, this cone will become closer and will be smaller and smaller. Okay, so now I want to show you some numerical experiments where we compare APM, the classical variant of the algorithm, the regularized variant, and our inexact proposal. So by matrix completion, I mean the problem of filling the missing entries of a certain matrix M. So we have a matrix M, say a square matrix. We assert only a small portion of its entries in all the entries with indices in a certain set omega, and we want to recover the entire matrix of the observed entries. And so you can formulate this problem as an affine rank minimization problem, where the linear constraints are here. So here, essentially, I'm requiring that the entries of X must be equal to the entries of M on the indices in the set omega. Okay, and so when you project on this set here, the projection is really trivial. We just need to set the entries of X as the entries of M. It's really simple. Here we consider two different type of experiments. So the first experiments are on Gaussian matrices. So we generate these matrices in a random manner, and then we assume to observe only a certain percentage of the pixels. And then in the second experiment, I'm considering one image. In particular, here I'm taking the truncated SVD of the lake image, so that we know that the image has a certain rank. In particular, it has rank equal to 30. Of course, these two images, these two matrices have different singular values distributions, and in particular, the image will have it will be much more ill-conditioned than the Gaussian matrix. So the first example with Gaussian matrices is, of course, a very simple example. Okay, so here I'm considering two different cases for the Gaussian matrices experiment. So in the first case, I assume to start the three algorithms, the two algorithms, APM and RAPM, from a good initial guess, which means that I'm starting from x0 equal to a matrix which is equal to the entries of M, where we know the entries, and 0 otherwise. And then y0 will be the projection of this point to the other set, the set CR. Okay, so here I'm showing on the left the heat map of this quantity here. This quantity goes to zero, where we have a good when the regularized algorithm is performing well with respect to APM. So as we can see here, so the black line is the one provided by APM, and the other lines are the one provided by the regularized version of the method. And so here we see that the heat map is symmetric. So that means that it is beneficial to choose the parameters equal. So lambda should be equal to mu. And in particular, we should regularize not that much in order to have a good results. In the second experiment here, I'm considering a bad initial guess. So I'm considering to take a 0 and y0 very far away from the solution. And here I'm showing on the left the results. The black lines is the APM variant, and the other ones are the regularized version of the method. And so you can see, so on the x-axis we see the radius.
Simone, ci senti?
Sì, yeah.
Ah, eccoci, scusa. Ti posso chiedere di stringere? Abbiamo poi...
I'm closing. Yeah. So
2 minuti.
Yeah, sure.
Okay.
I'm just saying that I just wanted to say that the regularized version here is more stable with respect to the choice of the initial guess, because you see here that as the radius of the initial guess is enlarging, which means that the initial guess is getting far and far away from the solution, from the intersection, you see that APM is falling in terms of percentage of successes. Here we are running the algorithms for 10 times. The regularized versions are more stable for an appropriate choice of the regularization parameters. Okay, and so here I'm showing you that APM, when fails most of the times, fails to recover a point in the intersection. In particular, here you have the black line, which just remains stuck in a local stationary point. And here APM is lower than a couple of regularized versions of the algorithm. And finally, here I'm showing you the plots for the test on the on the image, on the lake image, where we are comparing APM and the R in exact version. And you can see here that we are saving some computational time with respect to we are making some computational savings with respect to the iteration. In particular, the yellow line performs very well with respect to the other two. And so that's all. We presented a study where we compare the APM algorithm, the classical APM algorithm, with two regularized variants of the same algorithm, and we see that when the initial guess is very rough, our two variants, regularized variants, perform very well and in a more stable manner with respect to APM. We have several further developments, but maybe I can tell you something about it if you have some questions. So thank you very much.
Thank you, Simone. be close to you and be pretty impressed about your presentation. I see the very DNA of the conference in the slide you showed. You asked lots of possible applications also for the research topic following. Unfortunately, I think we are kind of in a rush for the final plenary session. Maybe I can suggest everyone, if you have any questions for the authors or the presenters, to contact by email or to use the session now to touch base with them. So thank you for participating in the workshop. Qua chiudiamo. Purtroppo la prima presentazione ha sbagliato tutto.